Good afternoon, everyone. Shortly, we will hear an interesting lecture by Olga Reznik on how to win the AR market. This is part of a webinar series organized by Photonics Israel on various aspects of photonics. The photonics industry is a technological and economic growth engine in the world. In Israel, it contributes about 6 billion annually to the economy. Photonics Israel operates within the Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to help foster new local and international collaborations. Olga Reznik is a physicist and an optical design engineer with 20 years experience in an optical design and optical system engineering, specializing in augmented reality and display system design. Olga's expertise is imaging, non-imaging, and illumination design. She's also the co-founder of Joya Team company providing optical system design services. Olga Reznik, the stage is yours.
Okay. Hi, everyone. My name is Olga. I'm from Joya Team. Today, I will talk about the topic of how to design the successful augmented reality systems. A little about myself and my team. This is the agenda I will cover today. What is AR? And how can it be used?
Olga, sorry for interrupting you. We need to see the whole image. You need to do a full display of the presentation.
I'm sorry. Oh, it's closed. No, I'm going to say share this one. Now it's better?
Now it's fine, thanks.
Yeah, okay. So again, to the agenda, I will tell a little about myself and my team. I will give you some introduction about what is AR, where can it be useful, a little about optical requirements formation process. This is our secret sauce. Key optical parameters of AR systems, definitions and examples. AR for medical application, test case, and a quick summary. You're welcome to ask questions at any points in the Q&A section, and I will try to answer as many as I can at the end of the presentation. So a little about myself. I have about 20 years experience in optical design in system engineering in Elbit systems, mostly for military applications, including helmet-mounted displays for pilots, which is the military father of AR and MR systems. Starting from January this year, I'm a co-founder together with my 3 friends and colleagues from Elbit of our own company called Joya Team. The experience that I can share is in optical design, non-imaging and illumination design, optical system engineering, displays design, and optical testing and photometry. And now introducing our company Joya Team is an optical technologies house offering optical systems development services. We are a team of professionals with about 70 years of collective experience in the augmented reality field. Our goal is to help our customers and partners to design exclusive tailor-made optical system. Our system development methodology approach covers entire optical system development process, starting from requirement definition and formation through all design and engineering stages to the prototyping and transfer to production. Our process integrates overall aspects, including imaging, non-imaging design, new technologies, testability, manufacturability, and cost. Today, we provide our services to customers and partners in consumer, AR, and VR market, in medical applications. We recently were involved in the FDA submission and certification of AR system for surgery. We also work with companies in the automotive market, in head-up displays, in LiDAR systems. We also work with various startups, from small companies to large corporations. Basically, everywhere we can bring our added value. So what is augmented reality? This term is used to expand the barriers of physical world with additional layers of information, like you see on this image here. While virtual reality technology replaces the real environment with an entirely artificial one, augmented reality adds onto the existing environments additional layers, which is done in order to modify and change the user's view of reality, which is transferred to augmented reality. These additions can come from different sources, such as textual information, synthetic graphic images or symbols, video for any kinds of spectrum, regular day video, night vision, thermal imaging, X-ray, and etc. So the augmented reality applications are only limited by your imagination. They started from niche applications like military helmet-mounted display systems, and then also the military use of head-up displays was adopted by the automotive applications market. And in recent years, this technology spread to various markets, including medical, enterprise, training, education, designers, and gaming, and everything. And of course, the golden ticket is naturally consumer market, potentially replacing our smartphones by smart glasses. I want to show you a short clip showing the use of AR systems in automotive market, different categories here. So. So what is my insight on the topic of AR system design? Many large companies with huge budgets and investments in the last years aspire to design new winning AR system. So why none of them really wins this market? Here are two most famous examples, Magic Leap glasses and Microsoft HoloLens. But there are many, many more examples of breakthrough AR sets that didn't reach quite their potential success. I think that what they're trying to do is to take the best technology available in the market or invent a new technology and create the best system that they can and hope to fascinate as many users as they can. One system to fit all users and markets, all use cases, etc. And there is a problem number one that I see, which is no system can fit all users and all needs. This doesn't even work in a simple thing like a suit. You have different events, which is use cases, and different sizes to fit different users. And when you have a tailor-made suit, it's a perfect fit. So this approach of one fit all surely cannot work in complicated products such as an AR system. The key is to focus on a specific market, use case, need, and the value you're trying to create. And then there is a point number 2. The better you understand the specific user needs, the more focused you are in the requirements, and the better system optimization and customization can be done. So I want to give you an example of our user-focused optical requirements formation process for AR system and medical application. So how do we start with forming the requirements for application like this? The requirements formation is a process that starts with the user and the user story and focusing on the specific user needs. What exactly the system has to do to help the user perform his task, and what the user would like to have that he doesn't have now, and how our system can bring this value. So then there is a dialogue between the user and the engineers that design a system, and the dialogue helps to get a deep understanding of the user and the use cases. This step is especially useful when the user doesn't understand the technical terms and engineering language, and the initial misunderstanding and misinterpretation can be cleared. And the next step is to translate the story to the engineering language and the correct technical terms. It often happens that people have a problem, but the root cause of the problem is not what they think that is. And of course, the last step is formulating the actual engineering requirement list with quantitative requirements, which is the base for the spec document. So in order to show you the importance of this and the impact of this process, I'll give you an actual example that we had with one of our partners in the medical application. The user specified the requirement, quote, ability to see both virtual and real objects clearly. So when we started a dialogue and wanted to understand what exactly this requirement means, we got a more clarified requirement. Virtual objects must be shown in the right focal plane, but this is still not a technical term. In the next step, we understood the interpretation of this requirement is the certain fixed focal length of a certain distance, which is the hand manipulation distance. But this is the requirement from the user aspect, while the engineering requirement from the optical system aspect is apparent image distance of 50 centimeters, which is, I will tell you more about this term, apparent image distance, in the next few slides. Another example that shows that even straightforward requirements like field of view are only clear when you're familiar with AR systems or optical terms in general. What the user sees as display area, which is large enough, must be understood in the context of his mission or use case, and then filtered or translated to appropriate technical term to formulate the engineering requirement that would satisfy the original user need. In this case, a specific field of view in degrees. So the last example stresses the often misunderstanding or misinterpretation of the root cause of the current painful issue. What the user experiences as neck pain as a result of neck bending after discussions and clarification is defined and covered in the engineering requirement that was not connected to the problem in the user's eye, but is clearly providing the required benefit, which is field of view shift down by a certain amount of degrees. This was, in short, the requirement formation process. And now I want to focus on key optical parameters that I want to provide you some basic understanding of them. So these key parameters define the performances of augmented reality system. We will talk about apparent image distance, MTF or CTF, see-through contrast, system pupil, and symbol accuracy. I would like to explain our interpretation of these terms. There are, of course, many more parameters that define the performances of AR systems, and this term are part of our optical terms library blog, and we see as our mission to create a common language and a sort of database that can be used by anyone who wishes to learn and understand the specific aspects of augmented reality systems. So I invite you to visit our blog so you can find out more. And I have a little story behind our logo here. So when you look at this logo image, it's very interesting to think what does it look like? This line on the side A, what does it look like when you look at it in the first, the first time you see it? Our idea behind it was to show an eye like it's drawn when you draw optical system with the pencil and paper. This is the symbol that shows the eye, and we wanted to have our logo to be an eye which is flashing a colorful light of all the spectrum. But when I showed this logo to my daughters, one of my daughters, I have 3, and she told me, "Why do you use a pencil?" And then I looked at it again, and I saw that it looks actually like a tip of a pencil, which is drawing in different colors. So it's like we are drawing with the colorful light. So this is also a good idea about this logo. So going back to our descriptions of terms, the first term that I want to explain is apparent image distance. In general, in augmented reality systems, a micro display source is projected using an optical system to infinity or finite distance. It means that a virtual image is produced. You can see here. A virtual image is produced by the rays. There are brain continues them and finds the interception point, and it sees the image located at this interception point. And the apparent image distance is the distance between the eye and this image point. So how do we tailor this requirement in case of augmented reality system? When the projected image is combined with the direct view, the distance of objects that you're looking at on the outside scene will determine the apparent image distance requirement. Like in this head of display simulation, you can see the objects of interest are in the close distance. So the image AID should match this distance so that both images are in focus. This is something that we learned from the users, pilots in our career, that complain sometimes about headaches and nausea and fatigue after using long-term of AR systems. And really, when we investigated this issue, we saw that they were suffering from constant accommodation between the different distances of the images. So this is something that we learned, and we try to imply it in our work. But when you project the image to the close distance, there is a downside to this, because this introduces a strong parallax effect. This effect is seen when the user is slightly moving his eyes and the projected image moves, losing the alignment with the outside world, the real objects, like you can see here in this example. So of course, this is not desired, because you want the images to be aligned all the time. Another requirement I want to explain about is the MTF or CTF. MTF is a commonly used term for image quality measure in optical systems. So MTF is a modulation transfer function, which is a system output contrast with the input of sign intensity profile, which is shown on this top part of this image. The NTF term was used historically mainly because it was more convenient to calculate, and it was a relevant term for systems using CRT displays in the past. But now, when considering AR systems based on microdisplays, this term can be replaced by a more appropriate term, which is CTF, contrast transfer function, which is the output contrast with the bar intensity profile input, which is shown on the bottom side of this image. So why I say that CTF is more appropriate? All displays have a pixelated structure, so the image has square wave intensity profile. So CTF better represents the system output contrast. And the highest system frequency, or Nyquist frequency, is when the image consists of 1 pixel on and 1 pixel off sequence, which is the highest frequency that can be produced for a given display. So CTF is the main image quality and sharpness measure. Then the higher CTF is the better. Like you see here, 2 images with high and low CTF. Of course, high CTF is better. So when we tell of the requirement, you should require CTF as high as possible. But on the other hand, CTF requirement come with the price of optical system complexity, size, weight, and cost. So some points to consider when tailoring the CTF requirement in order to create an optical design. In AR systems, it's very important to consider human vision characteristics. A very high CTF will just slightly improve the user experience, and in many cases, it's not justified. The second point is the image content. When the image content contains symbols or text, typically these elements line width is several pixels, and the CTF requirement for the Nyquist frequency doesn't bring any added value. But when a full video image is projected, the image quality of Nyquist frequency is important for the user to see a sharp and detailed image. So in our experience of almost 20 years in augmented reality field, we have put a lot of effort to refine these CTF requirements and tailor them to human vision. One of the tools we developed for system customization for human vision is the distinction of CTF and resolution requirements for different field of view areas. Generally speaking, primary field of view is most critical information is usually presented there. So the high resolution and CTF are required. And in secondary field of view, less important details are presented. So requirements can be reduced. And the peripheral vision is dramatically poor and they only used to create sense of immersion. So the requirements can be dramatically lower there. So this approach allowed the development of the first and only commercial aviation head-mounted system called Skylens, and we will talk about it later in a few slides. So the next term I want to explain is called see-through contrast. See-through contrast really expresses the ratio between the system internal luminance and the background luminance coming from the environment. So this term also expresses image color, since the background washes out the colors and they become less saturated and pure. So basically, this requirement should be defined for every primary image color to make sure that the color clearly is visible and is a sufficient brightness on the background. Now, see-through contrast is today one of the bottleneck parameters of AR systems for outdoor use. This is the point where many of the big companies that tried to win the AR consumers market failed. They couldn't deliver a clear and readable image in outdoor conditions. Many of them fell back to the less challenging indoor use. In our experience, we had a need to deeply understand this problem, to use our knowledge and creativity and provide working ideas and concepts that today are widely used in military and civil aviation and other applications. So what we learned is that defining the working environment conditions correctly is the first step to understand what is required from the projected image. And for a given background brightness settings, the see-through contrast primarily depends on microdisplay technology in terms of brightness, color, and polarization. The other part of the system that impacts the see-through contrast is the optical elements of the system and the proper combination and optimization of materials, coatings, and polarization elements eventually create the optimal working point when the goal is to get the sufficient and high enough see-through contrast with minimum power spent. So the next term I'll explain about is pupil. There are many different definitions of pupil, and I will explain two of them that we use. Eye pupil just represents the user's eye pupil size. So it is a reference parameter for performances evaluation, both in analysis, in optical design, and measurements in the lab. So this is just the eye pupil size in the drawing. And the system pupil is the area where the eye pupil may lie and where the performances are controlled. So this is the design requirement parameter. An optical design shall provide the required image performances and properties within the whole system pupil area. So when the user moves his eyes within this range, the performances will still be compliant to the requirements. So how do we tailor the requirement for system pupil? This is the system pupil defines the working space or motion box or area where the system can be used. So the larger system pupil is the better for the user. On the other hand, system pupil has direct and very significant impact on the system size, weight, and complexity. So on the other hand, the smaller system pupil on the other scale of this scale, other part of the scale, will result in smaller, lighter system, and then it would be more comfortable for the user. So actually, system pupil is a classical trade-off parameter, and it must be kept as small as possible to still be comfortable for the user. And otherwise, he will lose the crucial mission information during the operation, and this must not happen. System pupil can be reduced to the minimum using optomechanical compensations, like position stability issues are addressed by harness design, or personal fitting compensating for head structure and IPD differences, and some other techniques are used using head and eye tracking with the movable, adjustable elements in the systems. And now many companies try to break this trade-off, this traditional trade-off by there are some ideas of multiplying the pupil instead of making it larger. For example, you have Lumos pupil splitting patterns or diffractive or holographic elements in Magiclip or HoloLens patterns. These ideas may break this traditional trade-off, but they create a different one with different parameters that can still require some solving and some issues, and there are some unsolved problems there. So the last term I will cover is symbol accuracy. Symbol accuracy is image position and accuracy on the real world. This is important when the projected objects are overlaid on the real objects, and the alignment between them is important. Like in this landing approach simulation example, you can see on the left side, the air system image is clearly seen and on the landing route, and on the right side, the same image is poorly seen by overcast and in low visibility conditions. So the pilot performs the landing approach based only on the projected synthetic image. In this case, symbol accuracy is crucial for the mission because the user only uses the projected image to operate this mission. So if symbol accuracy is so important, how do we make sure that it is within the requirement? There are many factors that have influence on symbol accuracy. Among them are elements, manufacturing, position intolerances, see-through prismatic deviation, parallax, soundness instability, and you see the list is long. And when it's important for the mission, most factors can be reduced using calibration, mapping, and other correction processes. And there is always a trade-off between the calibration procedures and the production time and cost. The key of the successful optical system engineering job is to find the correct balance between the two. I want to give you the example of Skyline system for commercial aviation pilots that I mentioned before. Back in Elbit, we were the optical designers of this revolutionary system, and which is a good example of system engineering. I want to show you a short part of Skyline's image video that demonstrates the ability to fly and approach landing with almost zero visibility.
A window, and with enhanced vision, you'll be able to see the infrared depiction of the airport through that window. If visibility is good, the pilot would see with his own normal vision the runway environment through that window.
Okay. So quickly summarizing the key optical requirements and the major source of their requirements formation, I would say that apparent image distance and symbol accuracy requirements are mainly derived from use cases, while CTF, see-through contrast, and system pupil are mainly system engineering work and trade-off in search of optimal working point, something that comes with experience and deep insight. So I hope if you have any questions, I want to remind you that you can write them in the Q&A section, and we will try to answer them at the end. And now we understand better, I hope you understand better the optical terms and the requirements formation process. Let's go back and discuss the AR for medical application headset example. So we are talking about system that is designed for a surgeon that receives valuable surgery information during the procedure and displays the patient's X-ray. You can see here, image located on the exact position on the patient's body. So the X-ray image helps the surgeon to operate and perform the surgery accurately based on the data that he cannot see with his naked eyes. So if I want to cover the requirements that we talked about, the apparent image distance is clearly the surgeon's working distance. And I want just to stress that the numbers here are just for example, they are not the actual requirements. This is something that I added to show you the process. And the CTF for primary field of view is crucial. So we use Nyquist frequency, and the secondary field of view requirements are somewhat reduced. And for peripheral field of view, they are significantly reduced. And the see-through contrast will also be clear. The image has to be visible in highest scene brightness for all image colors for comfortable use. So far, it looks like there is no trade-off issues here. No parameters are independent. But when we discuss pupil and symbol accuracy, the picture gets more complicated. And system pupil has to be large enough to be comfortable for the user, so he doesn't lose the information, as I mentioned before. But because this system uses image projected to close distance, the large system pupil has impact on parallax, which also impacts the symbol accuracy. And in this case, in this application, it's very important to have symbol accuracy very low and controlled. So, the system pupil requirement was lowered in order to provide the more important design driver, which is the symbol accuracy. So this product that we discuss here is an example of how the tailor-made AR system design can give a value for the user. Of course, we just discussed 5 different key parameters, but there is a lot more, and the overall images are much more complicated, and the trade-offs are much more complicated in the real design. So this is quite a fascinating example of a very high value system. So what have we learned from this test case? During the stage of requirement formation, it's important to produce requirements based on the use case. And it's also very important to understand which requirements are the key parameters or performance drivers and which parameters are part of the design trade-off. And through the development, constant trade-offs and user feedbacks are part of healthy development process. And the important thing is to use this refinement process to find the optimal working point so the system gives the desired values. The trade-offs is word has like negative meaning for a lot of people because they want to have everything. But in fact, the best system is not the highest performance system, is just an optimal working point system. This process resembles of going back and forth with the user and refining the requirements and changing them in order to better fit the optimal working point. It resembles a diamond cutting and polishing process when cutting off precisely in smallest parts is a professional know-how that enables to get the most valuable stone. So thank you for listening, and I hope this was beneficial and you learned something. And I invite you to visit our website or our blog for more information. Now it's I hope there's time for questions, and if you have some questions or requests or cooperation ideas, you're always welcome to contact me or my partners, and we would always like that. And we see here questions. If you and should I, Roy?
Yes, hi, Olga. Thank you. You can see in the Q&A, you have several questions.
Should I read the questions?
Yes, please.
Any thoughts on a consumer-ready product, which will win in the end? I'm the only one who sees I should read the question?
Yes, you should.
Okay. Yuval asks if we have any thoughts on a consumer-ready product, which optics will win in the end, diffractive, reflective, holographic? This is a very good question, and like a $1 million question, maybe even more than surely more than 1 million. I think personally that diffractive and holographic technologies have many physical limitations there, and I'm not sure these limitations are something that can be, solved for the optimal consumer product. So I think less that it should be something like diffractive holographic, something more, I don't know, more simple maybe. Okay, I hope I answered. Thank you. I wonder what other AR implementation are in aviation. In aviation, you have the head-up displays, of course, which is high-end head-up displays, not the ones that use in automotive markets, but they are they have many years of expertise there. And you have virtual reality and augmented reality for pilots, both for military and civil now. There are other military that I know, but I'm not sure that I know any of other AR in aviation. No. This is what I know, like head-up displays and the helmet mounted displays in general. What is the difference? Someone without a name asks, what is the difference between ghost technologies in automotive and AR? In automotive and AR, there is no difference, I think, in ghost. Ghost is generally something that I didn't explain, but it's like an unwanted image that has some misleading information that can that was not intended, like a double image or something like this. I don't think there is a difference in the automotive or other markets. It's just something that is maybe the requirements are different because depends on the environmental brightness. Because when you're talking about like night vision systems, oh, I didn't mention the night vision systems, night vision goggles that have also for the previous question, the military. We have also designed augmented reality systems on night vision goggles. So you have, instead of the real environment, real scene, you see a night vision image and overlaid on that additional image with video or text or symbols or something like this. So going back to this question about difference between ghosts, so I think the main maybe the difference may come from different surroundings, different backgrounds. If you have a night vision system, then every photon is amplified in many times, so you see very, very low intensity ghosts and stray light, stray artifacts. Other than that, I don't. Maybe I didn't understand the questions, but if this someone who asked it, he can contact me later, so maybe I can answer better. So the next one is Eli. I mean signals of the signals of you were. This is a clarification for a different, I think, question. Signals of location, directors, weather conditions. I think that was regarding the AR in aviation, right? Signals of location, direction, and weather conditions. Yeah, in aviation, you use them both, of course. You have information about, some flight details, like height and fuel and the direction of flight and the nose of the, pilot and everything, and the directions, yeah, everything. So you're asking about the information that is shown to the pilot. So it depends, of course, on the application and what the user wants to see. And actually, they don't want to see so many things because they need to see, the real world. So it doesn't interfere them, it just helps them. So someone asked, can you tell me about Mura effects in AR? Well, Mura, it's Mura?
Yeah.
I think that that is if referring to Mura as a Mura, which is an effect of displays where, no? What is? Okay, I'm not sure about this one. Maybe you can contact me about this Mura effect in the email, and we can better understand the question. Okay, nice one. I was hoping that you touch a little bit of optical technologies. What is the most promising optical system technology that could help us achieve a good AR system? Diffractive, polarization, freeform, reflective, etc. Or a combination of them. It's all, like I said, the key is not to choose a technology, is to understand the use case and the user requirements, and then to match the different technology to this. But I think that personally, the simpler the design is the better. So diffractive is not my suggestion. Okay, and then someone asked about, oh really, Gil, why is it important to have both non-imaging and imaging design together in the same team when designing AR systems like you do? Okay, like everything that you design, when you have design separately some building blocks and then you add them together, then you have a potential mismatch between them. And when you design a system as a whole, it's always more efficient because the design can take into account all the aspects of a system, including non-imaging and imaging design, and there is a connection between everything. So you cannot do just optical design and say this is finished, and then I'm going to non-imaging, because then it's just like be analysis and not optimization. So it's a general thing that you have a system and you have different aspects, so you should take them into account from the beginning. So this is the better way to do things, including like here, my friends are helping me, including also thinking about testability and manufacturing and everything from the beginning, because it's a overall system, holistic approach. This is the key. Okay. Hello, Olga. Presentation is good. It's also helpful. Thank you. I have some doubts. I will mail you. Oh, thank you. You are most welcome to mail me and my partners. We always like to answer questions and help people. And if you have any issues you want to discuss, you're always welcome. We are here. Thank you for this. by system pupil, do you mean the iBooks? Yes, you have, yes, there are many terms that different people use for system pupil, and one of them is iBooks or motion box or iSpace. There are many terms that used for the same thing. Essentially, yes. Okay, so I think we're done here.
Yes, we are done. Thank you very much, Olga.
Thank you very much for this opportunity, Rui, and also Shlomo, who invited me to give this lecture. This is my first time, so I was very nervous and excited, and I hope you enjoyed it. And thank you.
Thank you very much, Olga. Thank you all for participating in the webinar. Have a good night.
Thanks.